here and share my screen and come over here. Yeah, so apologize again for missing the Wednesday class. I think my voice was starting to go out on Monday anyways, but that was the day that my now 2-year-old turned 2, and it was in the middle of singing happy birthday that the voice totally gave out. Apparently got a little carried away. So yeah, administrative wise, two things, the quiz we would have had on Wednesday being this coming Wednesday, and then the homework assignment that would normally have been due tomorrow being due Thursday instead. And there's the video posted about the details of that homework assignment. Any questions on those administrative things before material today?
The homework is due on this Thursday.
Okay. So I posted this topic 10 folder on the indexes and BTrees right here. The handout that looks like this, the final practice problems, you can find that in this folder here under questions in class.pdf. We'll be going over this file here today and Wednesday, maybe even into next week a little bit. And then there's a lot of PDF files that I have here that you all can use as review for the final exam. Basically, this last 2 weeks of, or the next 2 weeks of the course is going to be like what 80% of the final exam stuff is on. And so, yeah, what we're talking about is big picture idea. The idea of these indexes is, again, making our SQL queries fast. And so everything that we've been talking about has been sort of building up to this so that we can do this section. And you'll have one more homework assignment on the Twitter Postgres after this about adding indexes into the Twitter assignment so that you can do the queries like you were doing on the MapReduce, but have them take milliseconds instead of hours. And then the final exam will be mostly focused on these indexes thing. So this PDF file is what we're going over in class. There's this PDF file here just for your review outside of class. And I also have posted 2 previous final exams. Oops, not under the future, under the final folder. Oh, which I guess I didn't actually add to GitHub. I'll do that right after class. There'll be a final folder that has 2 previous final exams in it. You can take a look at for more practice problems, and the answer keys will be posted there, so you can take a look at that. So the final exam, roughly schedule tentative on like when exactly the baby comes, but we'll have the next 2 weeks of class, and then I'll post the final exam, and you'll have a while to work on the final exam. For those of you who are graduating this semester, that'll be the last thing in this class. And then for those of you who are not graduating this semester, there'll be one more homework assignment after the final exam as well. Any questions about anything administrative? What to expect? Okay. So yeah, this topic 10 indexes material here, I think is like, yeah, the most important stuff in the class. It's also the most abstract stuff. And so it's hard to have too much, I don't know, coding stuff or examples, concrete things. There'll be a lot of abstract sort of explanations about things. I will try to make those as exciting and non-boring as possible, but these will probably be, I don't know, hopefully not too boring, hopefully not too abstract, hopefully concrete enough to want to pay attention. So the basic idea here of our indexes, advantages, what we're going to see is that the runtimes of all of our select, update, and delete operations, They've previously been linear runtimes, O of n. Without indexes, they'll be O of n. And we're going to reduce this linear runtime down to this logarithmic runtime, log n. And throughout this document here, I have a lot of runtime notations where I'm being very careful about my use of the big O versus big theta versus big omega notation. Some data structures classes or previous classes only cover big O notation and not the other bounds, omega and theta. I'm curious, especially like Mud Pomona, is this the difference between O, omega, theta? Is this covered? Yeah, okay. Well, yeah, the intuition about, come here just for a second, just as a reminder, maybe refresher, intuition about the difference between O, omega, and theta. You should think about if we have like O of something, this is an upper bound. The omega is a lower bound. And the theta, technically it's both O and omega, but you should think of it as somehow like being equal. That the upper bound is like less than or equal to, lower bound greater than or equal to, and the theta is like being equal. And so over here, when I said that our previous operations take O of n, I really mean that it's only an upper bound. Sometimes it'll be just like a constant time, but worst case O of n. And we're taking that down to theta of log n. It will actually always be logarithmic, best and worst case, no matter what we're doing. And if I guess that details maybe not going to end up being super important, but that I have been careful about all my runtimes and bounds here, O and theta omega. Disadvantage of this. So this is a big speed up here, linear down to logarithmic, huge speed up. Disadvantage, we're going from insert time, previously constant, to now logarithmic. Still, both of these are very fast though, so not a huge penalty. The main references for this section, there's chapter 7 of the previous book that we talked about. And then this new set of blog posts here on haber.com. Haber is like a Russian version of Reddit. And they post a lot of technical articles here. It turns out that currently the best documentation for Postgres indexes is on this Russian website right now. And so that's what we're going to be using. All of this documentation was originally in Russian, and then it has been translated to English. So we're going to see a bunch of these index data structures. There are these techniques for speeding up our queries. This week, we'll be focusing on the BTree and all the different algorithms related to BTree. This is the most important of these data structures. And then next week, we'll be talking about all of these other indexes and when to use them instead of BTrees. But BTree is the default, and 99% of the time, what you'll want to be using and what you will be using. So before doing that, I want to maybe give us a little bit more intuition about why we're going to care about this. And so I'm currently, I've switched over to a terminal session here, and I'm in the homework assignment right now for this coming week, the Twitter Postgres parallel. And I'm going to connect real quick pSQL here to my PG normalized batch service. And what I want us to see is just that I have actually inserted stuff into this. Oh, I thought I had inserts. Well, let's go ahead and insert stuff into this database. So insert some things into that database. And yeah, that'll take a minute or two to complete. While that's going on, we'll take a look at this first page of the final practice problems here. Throughout the lecture today and Wednesday, we'll be going back and forth between answering some of these problems here and then just going over at a high level what the different SQL commands and data structures are doing. And hopefully the fact that we're looking at these questions will make the overview of the data structures themselves a little bit more concrete. If you look at the final practice problems from the actual finals, these problems are very, very similar. So if you can do all of these problems, you'll be set for the final. This first problem is the same for all of the well, you're definitely going to have this exact problem like word for word on your final exam. And what's going to be different is that the SQL code up here will all be a little bit different. And the SQL code up here is going to be based on the Twitter Postgres assignments on the normalized database somehow, where I've just selected some subset of the tables with subset of columns in here. And you'll have to answer all of these questions related to just this subset here. And so if we just scroll down to take a sneak peek a little bit later, you can see there's a handful of like select queries related to those columns. And we're going to be talking about on each of these problems, what do you have to do in order to make these select queries fast? This first problem right here talks about how there's certain constraints or parts of the table creation process that create these things called indexes. And so we'll talk about exactly what those are here in a little bit, but first we'll just talk about which one of these lines create indexes. And the only constraint that creates indexes is a unique constraint. So write that out. Only unique constraints create indexes automatically. IDX is a common abbreviation for index. And so here, there's one obvious unique constraint and a couple of less obvious unique constraints. So here's the obvious unique constraint right here. But then recall that anywhere you see primary key is equivalent to unique and not null. So anywhere we see this primary key, that's also creating an index for us. And so there's going to be 4 indexes that are automatically created in this table right here. And the corresponding commands will look like create index. And then when you're creating the index, it's always the name of the table. So we'll do this unique constraint right here first, the name of the table, users, and then the column list inside parentheses like this. So in this case, this unique constraint corresponds to username. So it'd be table users, column, username, like that. And then besides just username, in this users table, there's the ID users or id users. So users, ID, users. And then under tweets over here, there's the ID tweets. And then the last one here under tweet tags, tweet underscore tags. Here's a primary key. It has 2 different columns inside of it. First, id tweets and then tag, id tweets, and then tag like that, where tag is the second thing in this command over here because it's the second thing listed over here. We're going to see a little bit that performance-wise, id tweets comma tag is different than tag comma id tweets. They're different from a performance perspective, but not from a constraint perspective. Performance only. So the important thing about this first problem is just that you'll be able to list what are the indexes that have actually been created, because all of the subsequent problems are going to depend on these sets of indexes. And if you don't get this part right, you're definitely going to miss everything else. So it's only the unique constraints, again, that create an index. References requires a unique constraint on the thing that's over on the right-hand side, but it doesn't actually create an index. Not null doesn't create an index. We've seen what that does. It just, in the null bitmap, it affects what's allowed inside the null bitmap for each row. So we haven't talked about what the indexes do exactly yet. We've just talked about where these, what indexes automatically get created for us. Any questions about that? Okay. Question? Yeah. These are supposed to be semicolons over here. And so each one of these also has the create index in front of it. And that's supposed to be the end of the command. This one right here is a comma separating out id tweets from tag. And technically too, so these indexes, because they're corresponding to a unique constraint, if you were to create the unique constraint without doing it inside of the table up here, we would add the word unique inside of the command right here. So create unique index is how you would create a new unique constraint on this particular column in this particular table. For the purposes of like runtime analysis though, and the algorithms available, the unique here has no impact. It only affects the constraints. So whether you wrote for problem one, just create index or create unique index, either way would be full credit. The important thing is just getting the tables and the columns matched up over here correctly. Okay, so switching back over here, I want to take a look at what that looks like inside of our Postgres connection, connecting with pSQL. Let's rerun, select count star tweets. There's still only one tweet in there. Why is there one tweet in there? Because I didn't have from. So I had, this is what I had before, count star tweets. What this is equivalent to is this is naming this column right here as the tweets column, because the as keyword right here is optional. You can see up here the column header was named tweets. So this whole time I did have tweets already inserted. I just forgot to put the word from right there to make my select statement do what I wanted it to do. Select count star from tweets. And so we can see that we have 100,000-ish tweets inside of the database here. And this is enough that we'll be able to measure the runtime difference depending on whether we have these indexes or not have these indexes available. In Postgres, a common thing to do is measure how long your commands are taking, and you can do that with this \timing on. After you've run that, then it'll report how many milliseconds each particular command took to run the command down here. The next thing that we'll take a look at is there's a command called explain. Explain is a standard SQL feature, but the output of explain is not standard. And so if you're in SQLite or MySQL, you'll still be able to use this explain operator, but the output coming down here is different for every database. And so you'll have to just adjust on how to read it on a database by database level if you change databases. But the big picture idea of all the algorithms that we'll be talking about are pretty much available in every database. The output here, called a query plan, tells us exactly how Postgres plans on using different data structures, different indexes in order to perform the operation here. And so here, when we say select count star from tweets, it's going to do this thing called an index only scan on this index right here. If I do \d on tweets on the table, so \d, we've seen it for listing all of the columns of the table before. Down here below, it lists the indexes of the table as well. And so here we can see that there's an index corresponding to the primary key, which is this id tweets right here. This line right here tells me that it's a BTree index on ID tweets, this column right here. And again, that's because this is the primary key of the tweets table. Any questions so far? Okay, I'm going to change this from explain select star tweets. We have this operation here called a sequential scan, and then this operation up here called an index only scan. There's going to be a lot of bouncing and back and forth between our notes and pSQL here and the this file here today, and just because there's a lot of different things that are going to interact in weird ways. But the first things that we'll be talking about are the difference between a sequential scan here and an index only scan, and why this operation right here requires the sequential scan, and why this one up here is an index only scan, and what that means performance wise for us. So in order to talk about a sequential scan, I'm going to take us back over to this picture that we've seen before. This is the chapter 1 of that textbook, and it was showing us the pages, the format that tables are actually stored on the hard drive. And again, each table has a set of pages, and inside each page is where we store the tuples. And so when we do a sequential scan, it's literally just a for loop going over every single tuple inside of the table here. This is called the heap table because it has all the heap pages inside of it, and returning each one of these tuples that it finds. And there's sort of nothing that we can do better than this, because we have to select everything here, every column and every row according to this command. In our notes on the GitHub, if you scroll down here towards the algorithms for using indexes, there's going to be 4, and then specifically under this table scanning strategies, there's going to be 4 ways of scanning tables that we'll see. And these are 4 different algorithms for returning results from select queries that have this simple form right here. So where you're selecting from a single table with a simple where condition, which is may or may not be there. There's going to be 4 different algorithms here. And then as we add more things to our SQL statements, we'll be adding more and more algorithms on top of this. So the first of these possible algorithms is this sequential scan. And so this is something that can always be used. And let's talk about the runtime of this algorithm here. I have these 4 variables up here in A, B, and K defined, that I'll be talking all about all of our runtimes in terms of each of these numbers here. The in is the most important of these. It's the total number of tuples that we have in the table. So like over here in the tweets, when I do select count star from tweets, the output of this is that in value. So the in's like 100,000 here. In this case, the total amount of data that we have. And then we'll talk about each of these other values as they come up. But the in one here is the most important. And the runtime here, the table pages accessed, is always going to be O of in, because we're never going to access more than the total number of pages here. This K value here is the total number of rows that we actually return by the select statement. So I guess I didn't write a limit K clause up here. So I probably should have taken out this omega of K here. But if we have a limit K clause here, then that'll force us to see at least K tuple pages. When this sequential scan is going to be used, at this point, it's sort of our default situation when no index is defined. Yeah, so we'll see some of these other situations here in a little bit, but this is sort of the default algorithm, something that, that you can always use. What we'll go on to next is the structure of the BTree, and then the simplest of these BTree scans, which is this index-only scan. We'll see how it compares to the sequential scan and why it's being used over here. Any questions about the sequential scan, though, before we go on to the BTree? Okay, so the BTree is moderately complicated. For the purposes of our class, you'll need to have a relatively intuitive understanding, but not low-level details. It's implemented in C, does a lot of weird memory management and hard disk access stuff under the hood. You won't need to know those things, but you will need to know like high-level, picture-level understanding of things. That blog post over here on Haber has a picture of a BTree right here, and this is a pretty standard picture. The basic idea of this tree is that it is a balanced search tree, but here you can see that it is not a binary search tree. So in your data structures class, you probably talked about binary search trees. I like the AVL tree, but other professors like red-black trees or 2-3 trees. And you probably implemented this. What we're going to see is that these are good for in-memory access of information, but they're not good for hard drives. So BTree is an extension of these search trees designed specifically so that the data can be stored on a hard drive and efficiently accessed. The key idea of that is that in order to quickly find information, or that it is fast to find information, that it's stored close together, but it's slow to seek to find new information on a hard drive. And this is true both on what we call HDDs, hard disk drives, and the solid state disk drives. But it's especially true on these hard disk drives. And I have an actual 2 hard drives here that I have taken apart and you can play around with so that you get a better sense of these things here. One of them is a solid state drive, and the other one is the hard disk drive. And what you'll see here is that there's this spinning platter that actually stores the information on the hard drive itself. And then there's this little arm here that actually has to move back and forth anytime you're accessing new information. And this arm has to like physically move about 1 inch or 2 inches in order to access new information. Feel free to actually like push it around and move it here. And that takes a surprising amount of time to do that. There's this website right here from a guy named Peter Norvig. Norvig is the pretty famous AI researcher. He's currently the head of AI at Google. And when he was in charge of interviewing people at Google, he basically made all the people he interviewed, he would ask them questions about like, how long does it take for certain computer operations to happen in practice? And so essentially required people to have this table right here memorized. The important thing about this table right here is that if you're executing a typical instruction, so like comparing if 2 numbers are less than or greater than each other, that takes about 1 nanosecond to do. But if you are fetching from a new hard disk location, so actually having to move that little arm on the hard drive, that takes about 8 million times longer than doing a comparison operation. So because this operation down here takes so much longer, moving that arm physically on the hard drive takes so much longer than executing actual CPU instructions, the BTree is going to be optimized for reducing the amount of movement on that, that armature. Let's see, it also turns out that, so on the hard drive, you can't physically see how it's divided into these little sectors here. But they're divided into sectors, and typically those sectors are 8 kilobytes, matching the size of pages on Postgres. And so that's why Postgres chose 8 kilobytes as its size of pages. If we take a look back here at this picture of the BTree, I'll describe what's going on in this picture here, and then we'll talk about some of the algorithms that go on with this BTree, and that'll hopefully give us a sense about why the BTree is structured that way. And then we'll talk about some of the runtimes of these algorithms, and the runtimes will be relatively long, complicated formulas, but we won't go over like a detailed analysis of those, but looking at the pictures will hopefully make it make sense about why those formulas are the way they are. So in Postgres, each one of these boxes right here is a single one of our 8 kilobyte pages. And then each one of these little circles inside of the box is a single piece of information inside of the page. So essentially like a tuple. Each one of these pages right here, even though it's inside of an index, it's structured the same way that the pages of our heap table were structured, where there's a header at the top, and then these little pointers here, and then the actual data down here. Inside of the index, the only information that goes into the index page is whatever the information is inside of our create index command. So right here, when we say like create index users of username on this line right here, the corresponding tuple that's inside the index page will only have the username information inside of it and will not have any of the other information about the users table. So we have a key, or we have an index on id users right here. That id users is in the index, but this created at and this username are not stored in the index in any way. Instead, what the index is physically doing is it's storing these TIDs, these tuple IDs, next to each of these key values. So inside of the index here at one location, there's a key equals queen, and then the tuple ID, which again is a combination of two numbers. The first number is which one of these pages were inside of it, and then the second number is which tuple inside that page. So based on the tuple ID right here, I can in constant time access an individual tuple. And so knowing that this is the 7th page, tuple 2, in constant time, I can get the information out of this tuple. And then I can find this particular key right here, this particular tuple ID corresponding to the key of whatever I'm searching for. We'll see how to do that in logarithmic time using the index itself in a little bit. But so here, all that's drawn in these pictures are the key values that correspond to a particular create index command, but it's not showing the tuple IDs, but those are also stored here in the page. Actually, so here there's, with most of the binary search trees that you probably talked about in your data structures class, information was stored both in the internal nodes of the tree and in the leaf node of a tree. For a BTree implementation, as done in Postgres, the tuple IDs are only stored in leaves down here, and any non-leaf node, so any internal node up here, does not store tuple ID information at all. This information up here only stores the keys. And then down here, so like if we have 4 going on to the left, 4 is the smallest number over here. This is going to be one of the entries in our table somewhere. The tuple ID is stored down here, but not stored up here at all. The couple key vocabulary words is the first one is the fan out of a BTree. So I'll write that out here. The fan out of the tree. And what the fan out is it's the number of nodes or the number of tuples stored inside a node. And so up here, we can see that the fan out this particular node right here is 3 because there's 3 tuple values inside this node. And so that means there are 3 corresponding children down here. Each one of these nodes, they all happen to have 3 fan out, 3 internal nodes. And so this is like as evenly balanced as things could possibly be. The insertion and the deletion operations inside of BTrees, we're not going to go over them in detail, but they ensure that the fan out always remains relatively balanced, although it won't be exactly balanced. And so the entire tree will be balanced like this. But in general, the fan out of individual nodes not guaranteed to be exactly equal. For Postgres BTrees, typical fan outs. So let's say our page size again is 8 kilobytes. If we have a BTree that's created on a relatively large type, so like the big int type, we've seen before that has a size of 8 bytes. So we can store approximately 1,000 big ints inside of a single page, neglecting the header information. So 1,000 big ints per page. So it's common to have our fan out in a Postgres BTree is going to be on the order of like maybe 100 to 1,000. So relatively large fan outs here. The fan out, again, of the balanced binary search trees that you've probably implemented before. Binary search tree is just equal to 2. So these we might also call these much fatter and shorter data structures. Turns out the height of a BTree is going to be equal to the log base B of in, where B is our fan out. And the in value up here, again, is our total amount of data in the tree, or total data in the index. Again, the B tree is going to have much larger B values than like the binary search trees. And so the height of the B tree, a larger B value here, it's going to have a shorter height, a shorter height than the binary search tree. Any questions so far? All admittedly a little bit abstract still at this point. Okay, so then why do we care about this? What's the key reason? Why do we use the B tree? The answer is that the total number of disk accesses that we'll have to do if we're looking for a single number. So if we're, say, looking for the number 20 over here, the total number of disk accesses that we'll have to do is equal to the height of the tree. That will first load up this this page right here, and we find which number is 20 between. 20 is between 4 and 32, so we'll go over here to the left. 20 is between 4 and 16, or sorry, 20 is between 16 and 25, so we'll go down to the middle one right here and find 20. We only have to touch the total number of pages equal to the height. So shorter height than the BST implies that fewer nodes are accessed. Again, with the typical fan out of a B tree in Postgres, with your base value B here being only, or being like on the order of 100 up to 1,000. Your in value here is going to be, even if you have something like, if say in equals 10 to the 10th, so it's like a huge table here. That's 10 billion rows in your table. If our fan out is equal to 100, then the height of the tree, the log base B of in, the log base 100 of 10 to the 100. I think that's like 4. And so there's only 4 nodes that we'll have to access, 4 disk reads that we'll have to perform in order to find whatever we're looking for, to see if it's inserted into the table. The total number of comparison operations that we'll be doing. So a comparison operation is checking to see whether a number is less than or greater than another number. Inside each of these nodes, we'll have to compare against every element inside the node. So the total number of comparison operations that we do is proportional to the fan out. But the comparison operations, again, extremely quick. Write this out. Total comparison ops is proportional to the fan out. So those increase when the fan out increases. But the comparison operations, again, that's just a single CPU instruction checking whether something is less than or greater than. So this happens on the order of like 1 nanosecond. And the disk accesses up here happen on the order of 100 nanoseconds. So we really care about minimizing the disk accesses much more than the total comparisons. Combining all of that information together, if we come down here to our next index scan type, so talking about the table scanning strategies, again, the B here is the branching factor of the B tree in number of tuples in the table. Then in what's called an index-only scan. An index-only scan is one that only has to look at the index and not the table at all. See details of that in a second here. But the index pages that get accessed here is this formula right here, the theta log B of in plus this K over B if we're returning multiple values over here. And the comparison operations right here is B times log base B of n. As B increases, this number here grows. So the optimal value to reduce the number of comparison operations is 2. But again, we don't care about the comparison operations since we're storing things on hard drive. We care about the number of index pages accessed. And so we want a large fan out factor. And generally, we want the largest fan out factor that we can have. Okay. So exactly what is an index-only scan? What's going to happen in an index-only scan? If our, say we have a search by equality condition, so inside of our where clause, we have something that looks like index field equals expression, then we will go through here and find all of the tuples that match that equality here. So here we're looking for the number 49. 49 between 32 and 64, between 43 and 49, so come down here. And then the B tree, all of these leaf nodes down here, they have links to their subsequent leaf node. So when we're at 49 right here, we can just jump straight over to the next leaf node over here, 49, and we'll get the all of the things that match our equality condition. And again, it's the tuple IDs down here that are being directly stored. In an index-only scan, we don't actually need any information from the table. All that we're looking for is counting for, or all that we're looking for is contained in the information of the index itself. So I'm going to jump back over to, here it is. Here, if I'm doing a select count star from tweets, we'll add a where clause here, something like where id tweets equals 5. This isn't, we can implement it using an index only scan here, because I'm not actually trying to return any information from the table right here. I'm just have an equals clause right here that scans through this index. This index again was created automatically for us by a unique constraint, and then it'll count how many tuples in the index match that constraint. In this case, none of them are going to match it because that's too small for our id tweets. And so it runs very fast here in logarithmic time. If we did not have that index, then rather than running in logarithmic time, it would have to loop over everything in the table. And so it would take linear time here and be slower. I'll do an example of that in, well, I'll do the example right now and then stop for questions. So if we do \d of tweets here, we only have an index right here. So here we have 3 indexes right here. The only BTree index we have is on id tweets right here. We don't have an index on id users at all. And so if I wanted to do a select count star from tweets where id users equals some number, then I'll have to actually scan over the entire table right here because there's no index that contains this id users column. So it's doing this sequential scan right here. We can see that, so this operation here where it's actually computing it takes 36 milliseconds to run right here. I'm going to create an index on this column though, so it'll be able to use the index only scan, and then we'll see that runtime will drop down really fast. So I'll do a create index on tweets id users like that, semicolon, and then rerun the explain command. And now it's able to do this index only scan right here instead of the sequential scan that we had before. And if I take away the explain, it'll actually compute that. And you can see that it runs in under a millisecond instead of the 36 milliseconds that it previously took. Any questions so far? How's everybody tracking? Is this too easy, too hard, too boring, too fun? Why does not everything use to be?
Primary keys. Why wouldn't you just make more features if it's so much faster?
Oh, so the primary key automatically creates the BTree index.
Okay.
So here and so yeah, this is a maybe part of the question is we're here coming back here under tweets, id users here references the users table right here, and it's you almost always want, when you have a references like this, you'll almost always want to actually manually create an index on that corresponding column right here. We'll see when we do joins that, or we have seen with joins that it's very common to join columns that are foreign keys like this. If you don't go out of your way to create that index, then that join will be really slow. If you create that index, then the join will be fast. So it's sort of good practice just to create indexes on all of these things with foreign key constraints. I don't know if that was at all related to your question.
Yeah, I think I just didn't exactly know what the features like automatically.
Yeah, that's what the yeah, I need, so the shortcut thing to remember, if it's a primary key or if it's unique, it's going to have the BTree created for it. Question?
Yeah, I think I'm still a little confused. So it doesn't have an index.
If there is no index, it must do sequential scan.
But like, wouldn't it be faster? Like, I guess because when you select counts rather than ID or something, and that's using sequential scan, like, wouldn't it be still be faster?
So in order to use an index scan, the index must exist. So yeah, you're right that, so like here, we just saw this users equals 5. That is faster with the It's faster using the index scan right here. But the only reason we can do this index scan is because this index right here exists because I just created it. If I remove that index, so drop index, that thing right there, then it no longer exists. And so now there is no index that stores inside of it this column anywhere. So there's nowhere for it to look except looking in the table itself. And so it has to do the sequential scan right here.
So we can utilize it.
Yeah, so the question is, are there times when the sequential scan would be faster? Let's think about our condition here. What if I change this id users to id users is greater than 5? So now this is going to match a significant fraction of the table right here. And I don't have index, create the index. Here we'll see that it's actually still using an index only scan in this case. Sometimes Postgres would prefer to do a sequential scan instead of an index only scan if it thinks it has to scan the whole table anyways. It will do that sequential table scan. Here, I don't think I mentioned it with the BTree. One of the nice things about the BTree, because the bottom is all ordered down here, if you are doing like a greater than or less than query, then once you find either the smallest or the largest in that query, you can just keep going to get everything else. And so the BTree index is, so the search by inequality section talks about that. If we find the 32 is the largest, you can still get everything in that range with the index scan. Internally, yeah, Postgres has some complicated algorithms about picking which. So just because it can use an index scan doesn't mean it's guaranteed to use an index scan. Postgres will determine for you automatically which one is faster and use the one that's faster. Please. Yeah, question is, why would you not want to create as many indexes as possible? And there's two answers. They're sort of the same answer. But the first answer is that up here, that the runtime of our insert operations goes from constant time to logarithmic time when we create an index, because now rather than just directly inserting something into a table, we also have to maintain that index data structure. So there is more overhead. And especially when you are inserting, or if you had, say, like 1,000 indexes, then that overhead can start to add up. Those data structures also take up disk space, so maybe you'll run out of disk space having too many indexes. And we're also going to see that, so this query down here, or this query over here that we were using, where did it go? Here we go. This query is like about the simplest SQL query possible. That the sort of SQL queries that you're writing for your Pagilla assignments, they would not be sped up by these very simple indexes. We'll have to be creating very complicated indexes in order to do that, and creating all of the possible very complicated indexes. It has sort of like an exponential growth on how many to create. And so you really have to tailor your index creation to the particular queries that you're interested in running. But yeah, so that's like the key performance thing about Postgres or SQL in general and indexes is figuring out what are the right indexes to create for your queries. And that's really what we're going to be talking about over the next 2 weeks. We have all these sample queries down here that do different things. And so then the questions will be, what are the right indexes to create to make all these queries go faster? Question?
Yeah, and then also, if you delete a table, do all the indexes that are related to that table?
Yeah, so if we drop a table, so if we did something like drop table tweets right here, it would also, I'll go ahead and do that in a transaction so that I can undo it, drop table tweets like this. You can see that it's objecting to that because there are other things that depend on that table, like these indexes here. If you add this word cascade to the end, then it says actually drop everything and everything that it depends on. Good questions. Okay, so these are the two simplest scanning techniques, the index scan and the index only scan and the sequential scan. The index scan is next, and that's a little bit more complicated. What happens in an index scan, so let's do \d tweets again. We'll see that we have two indexes now, this id tweets and this id users. And what happens if I want to do something like select the text from a tweet, select text from tweets where id users equals whatever the number is right here. This text column right here is not contained inside of the index in any way. And so when I do this, you'll see here that it says index scan instead of index only scan. The difference between an index scan and an index only scan is that in an index scan, there's information that we need for our answer that is not contained in the index. And so in this case, we will get the tuple IDs stored in the BTree and use those tuple IDs to look up the information in the original heap table. So an index scan, for some reason, there's information that we need that is not contained in the index. And so we need the tuple ID itself. Here, if I change this to say count star, that can be an index only scan because now the only information that we need is contained in the index itself. If I change that to id users, again, index only scan because this information right here is contained inside of the index. If I do so \d tweets again, recall that we have two indexes, two BTree indexes, one on id tweets and one on id users. The index scan is not able to combine two different indexes together. So if I were to search for id tweets, get the id tweets information out of with id users like this cannot do the index only scan. It'll use the index scan on id users to extract the tuple IDs to get the id tweets down here. The performance-wise, the difference between the index scan and the index only scan is the number of table pages accessed. In the index only scan, the number of table pages accessed will be 0. In the index scan, the number of table pages accessed will be theta k. You'll access exactly one table page for each tuple that you're returning here. Otherwise, the total of index pages accessed and the number of comparison operations is exactly the same. If it's possible to do an index-only scan instead of an index scan, the index-only scan is guaranteed to be faster, so Postgres will always choose to do the index-only scan instead of the index scan. Any questions about the index scan? Okay. The last scan method is called the bitmap scan, and this is the one that is the most complicated, and there's a handful of different sort of explanations about when you would use the bitmap scan. I think the simplest of these explanations is that if we have an and or an or clause in our search, then you probably have to use a bitmap scan. So what the bitmap scan does, and I'll draw a picture of this. For each index that it scans, it creates a bitmap, so just a list of zeros and ones that correspond to all of the tuples in the table, a 0 indicating that it's not a result and a 1 indicating that it is a result. So for each index, creates a bitmap of 0 and 1, where 0 indicates not in the index, not in index, and the 1, sorry, not in the table, not in the results. and the 1 is in the results. So this is a relatively complex or a relatively expensive operation right here, because this is going to take time linear in the total amount of data that you have. Generating this bitmap right here. It's linear in the total amount of data that you have. And then it combines the results of these different bitmaps using the and or operations. Combines these results using the binary and or ops on the individual bitmaps. So if we had a table that has so our id users and id tweets, and let's say we have like id users here, 5, 5, 5, 6, 7, 8. Id tweets over here, 1, 2, 3. These are lined up. 3, 4, 5, 6. And we want to get our condition here that we're searching for is id tweets greater than 2 and id users equals 1. Then we have two different indexes, one created on the id tweets, one created on id users. For each one of those indexes, we'll create this bitmap that satisfies each of these conditions. So here, id tweets greater than 2. So this will be 0, 0, 1, 1, 1, 1 for that corresponds to this condition right here. And then this condition right here will be 1, 1, 1, 0, 0, 0. When we AND those two conditions together, the result would be 0, 0, 1, 0, 0, 0. And then we will only get the tuple ID for this particular ANDed result right here and look up that in the actual table. So only look up this in the table. So for both indexes, we basically have to scan everything in the index, look at all entries in the index, but we can potentially greatly reduce the number of locations in the table that we have to look at using the AND here together, that both of these or each one of these conditions by themselves selected a large fraction of the table, but ANDing those two conditions together selects a very small fraction of the table. And so it means that we only have to do a small number of page lookups to do this. If we come back over here in our P-SQL environment, that in order to make something like a bitmap scan happen, we'd have id users equals 5 and id tweets equals 10, something like this. And in this case, it's still preferring to do an index scan because it's not going to have to do the entirety of the index. It would now have the option, though, if it wanted to do it, of a bitmap scan. It's a little bit awkward to force a particular algorithm on Postgres. Postgres has these internal data structures trying to, or internal heuristics trying to predict which one of these is going to be faster. So it's choosing to use an index scan now, but it would prefer to use, or it could use the bitmap scan at this point. So that's the main reason when a bitmap scan is used. So here's what I wrote out previously, our high level idea of what the scan is doing, computing the and or the or of the bitmaps after it's computed them. We use it if we have multiple indexes that will be consulted, that's the time to use it. Or if K is relatively large, the total number of pages that we're going to be returning is relatively large. The reason why this is an important factor right here is with the index scan, the total number of pages accessed is always going to be theta of K in an index scan. But importantly, theta of K is potentially much larger than the total number of pages in our table. That the number of pages is n divided by A, and K is only upper bounded by n. A here is the total number of tuples per page in the table. And the index scan is just returning us tuples one at a time. And so if those tuples happen to match into the same page, Postgres is not able to cache that. It has to look at all of them. I don't have my thing. This is good enough. I don't want us to miss out on the video lecture. This is a good stopping point for here. Next time, we'll review some of these index scans a little bit more, and then go on to the more complicated SQL queries and how they relate to indexes. If anybody has questions about any of those things, happy to